Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh to the lecturer NTIR Mazlan bin Mansor and to my friends, Aiman Affandi. First of all, so today we are going to present the project that we are assigned, which is the torsional loadings evaluation from actual stress solid mechanics mini project. For introduction, basically the purpose for this project is to evaluate proportional loading from a structure that apply torsional loading that can be found around us. After identify the structure that we can find nearby, we choose a scissor car jet to do the evaluation. In this project, we has draw the details such as FBD free body diagram from the scissor jet and solve the related problem. With the FBD, we are able to develop equilibrium equation also with the full analysis from the structure. So I pass to Mama Aiman Affandi for the structure concept.
Okay, Assalamualaikum and hi, I am Mazlan. I hope you are in a good condition. So I will explain about the structure concept of scissor jack. So scissor jack is a mechanical device that used to lift a vehicle easily off the ground by using manual manpower. There are four arms in scissor jack, which are connected by a power screw. A scissor jack have a diamond shape frame with a nut at one side and a sleeve on the other side, and a sleeve on the other side. The nut and the sleeve are supported by a screw. When the screw is rotated, the nut moves away or towards from the sleeve depending on the direction of the rotation. The rotation either will lift up or lower down the vehicle which is supported on the scissor jack. So I pass here to my friend to explain the next slide.
So for this slide, we are going to show the original structure for the scissor jet, as you can see in this picture. So this picture is about in this picture, Affandi has measured the length of the crank, which is equal to 260 millimeters. So we are going to uh, we have researched that this material, the material for the scissor jet structure, they use carbon 45 AISI 1045 steel. So for the elastic modulus is 201 gigapascal, tensile strength is equal to 530 megapascal, shear yield strength which is half of the tensile strength equal to 265 megapascal, uh, power screw shaft length which is in this scissor jet structure, we get 400 millimeters, and for screw shaft diameter, which is 2C, is equal to 9 millimeters, and crank length, as mentioned earlier, we get 260 millimeters. The length of the arms from hole center to hole center, which is L, is equal to 45 millimeters. From base to top, the length from base to top at minimum raising height of the jet, which is E, is equal to 180 millimeters. And normal working force applied on crank on this crank is equal to 49.05 Newton, and maximum load on the top of the carrier, which is a quarter of the, we assume a quarter of the car weight, which is equal to 5,886 Newton. And for the angle that we measure or assume is equal to alpha equal to 51.6 degree. So for the idealized model, you have to note that, as you can see in this picture, there is no screw thread. So the calculation of the threads of power screw is neglected, which means the power screw works with 100% efficiency. So we are going to the next slide. I will pass to Muhammad Aiman Affandi.
So I am going to explain the free body structure, a free body diagram of process and equation of equilibrium. So we can look at the simplified mechanism at the joint of the top of section, which is we can calculate the submission of fx equal to 0. Then f1 sine alpha minus f2 sine alpha equal to 0. So f1 sine alpha equal to f2 sine alpha. Then finally we can get the f1 equal to f2. Then we go through to the submission fy equal to 0. Uh, f1 cos alpha plus f2 cos alpha minus f equal to 0. Then the 2 times f1 cos alpha equal to f1 equal to f2 cos alpha. Then we can get f1 uh, equal to 5886 times 2 cos f 51.6. So finally we can get the f1 is equal to f2 at the amount 178 Newton. Then we go through to the point of the components at the joint of the screw shaft and arms to the submission of fy equal to 0. Then f1 times cos alpha minus f3 cos alpha equal to 0. So f1 cos alpha equal to f3 cos alpha. So that f1 is equal to f3 at fy. Then at the fx, the submission of xx equal to 0. So the fourth is f1 sine alpha plus f3 sine alpha minus fs equal to 0. Then fs equal to 2 f1 sine alpha. Then fs equal to 2 times 4738 that we got from the figure 4 times sine 51.6. So the fs is 746. So basically, the angle is decreasing at maximum rising height of the jet. Consequently, the maximum force is decreased. Since the maximum loading force will act at the minimum rising height of the jet, the design stress will be analyzed at that point. So, due to the symmetry structure, we can conclude that F1, alpha F1 equal to alpha F2, then equal to alpha F3, equal to alpha F4, and equal to alpha F1 prime equal to modulus F2 prime equal to modulus F3 prime and modulus F4 prime. Then the next slide, I will pass to my friend Redhuan Amar to continue.
Okay. So for the last slide is we are going to analyze and discuss the forces acting on the structure. So for shear stress, first we have to find the polar moment of inertia which for solid shaft, because the power screw is for the structure is a solid shaft. The polar moment of inertia is equal to pi over 2 times c power of 4, which is equal to pi over 2 times 4.5 times 10 uh, power of minus 3 power of 4, which is equal to 6.44 times 10 times 10 power of negative 10 meter power 4. And so for moments of equilibrium, as we can see in the picture, the moment of equilibrium for power screw. So the rotation for rotation clockwise rotation moment is negative. The summation of moment at y is equal to 0. So so the force so the force acting on the crank times to the length of the crank minus t is equal to 0. Then the torque the acting on the power screw is equal to 12.75 Newton meter. And next we are going to find the allowable shear stress. So for allowable shear stress, uh, is equal to torque times C over J, the polar moment of inertia. Then we get the allowable shear stress equal to 89.09 megapascal. So for the maximum force that we feel the structure, first we have to find the maximum torque, which is equal to allowable maximum shear stress times J divided by the C, which is equal to 37.92 Newton meter. Then only then we can find the force, the maximum force, which is equal to maximum torque divided by the crank length, which is equal to 145.85 Newton, 145.85 Newton. So next we are going to find, and lastly we are going to find the factor of safety. So for the factor of safety formula, which is equal to fail shear stress or maximum shear stress divided by the allowable shear stress. So we got that 265 megapascal divided by 89.09 megapascal, and we got the factor of safety equal to 2.97. And according to we have researched the internet, according to general value of factor of safety for lifting equipment, the safety factor of the scissor structure, especially the power screw shaft, should be from 2 until 3. Thus, the design of the scissor jet for lifting are safe unless the allowable shear strength exceeds the value of the maximum or failure shear strength. So we can conclude that if the shear strain divided by maximum allowable stress is between 2 and 3, then the scissor check is safe to operate. I think that's all from us. And now, before I end this presentation, I want I want to thank the IR Mazlan Mansor for guiding us throughout this project in regarding the calculation and the theory. So I think that's all
Thank
from
you, sir.
us. So thank you, sir. Bye.
Assalamualaikum.